All right, welcome everyone. So let's get started today. Hopefully everyone's Thursday is going well. Today we're going to continue on with our talk about continuous functions and see how those are related to limits. And we'll finish that up, and then we'll move into limits at infinity. So, we'll see what happens when our input x gets larger and larger positive. All right, so let's continue on though first with continuous functions, and this is where we left off on Tuesday. So when we were finishing up then, we saw a list of elementary functions that are sort of the building blocks for the course, and we saw where each of those functions is continuous. So what if we're going to see these functions over and over again in the course, so it's good to see this exposure. And what did we see? Polynomials, rational functions, trig functions, inverse trig functions, exponential functions, root functions, log functions. So we had this list, and we saw where each of those functions is continuous. So we had, all of those functions really work nicely. They're continuous on their domains. And for a lot of them, that means just all real numbers. So those are sort of the building block functions that we're going to work with. And what we're going to see today is, well, we can combine them to form new functions, other functions. All right, so how can we combine them? Well, with just usual arithmetic. So we can add two functions, we can subtract, we can multiply by a constant, we can multiply two functions, we can divide two functions. And the nice thing is, when we do that, it works very nicely with continuity. So if we add two continuous functions, the result is continuous. If we subtract, the result is continuous. If we multiply two continuous functions, the result is continuous. And so really what this theorem says is that doing arithmetic preserves continuity. And the only one we have to be careful of, and as soon as you see division sign, you know this is something to be wary of, is division. So we can divide two functions as long as we're not dividing by 0. So that's the only sort of asterisk here, is that we do require our denominator, that's g. So we require our function g, it can't be 0. That's the only requirement. We can't divide by 0, and we know that already. And if we do divide by 0, well, what happens is then we're introducing a discontinuity. So besides that, we're free to add, subtract, multiply, and divide continuous functions, and the result is continuous. So let's take a look at this example. We have this function f of x equal to 3 times natural log x plus inverse tangent x divided by x squared minus 1. And we're going to figure out where this function is continuous. So we're going to figure out the interval of continuity. And so let's start with the function. Let's start with f of x. Or let's start with that natural log function rather. So we're going to just talk about natural log x. And this is one of our elementary sort of building block functions. Where is that function continuous? Well, we said we had it on our list. It's continuous on the interval from 0 to infinity. So natural log, is continuous. There's no breaks or jumps in its graph on that interval, 0 to infinity, the open interval. Now, what about if we look at this? In the numerator, we have a 3 times natural log x. And what are we doing there? Well, we're taking our natural log function, we're multiplying by a constant multiple. So that's sort of this property here where we're multiplying a function by a constant multiple. And what happens to continuity? Stays the same. So the interval of continuity for 3 times natural log is just 0 to infinity. Now what about the other function up there, the inverse tan function? Well, this is one of those nice ones where it's just continuous everywhere. So it's continuous on the interval from minus infinity to infinity, the whole real line. So there's no restriction on continuity there. And then to combine those, what are we doing? Well, we're adding them in this function. So that's how we're getting the numerator. And to find the interval of continuity for their sum, we have to go with the most restrictive interval. So we only use the numbers that appear in both of these intervals. So we kind of have to go with the most restrictive. And so in this case, even though inverse tangent is good everywhere, that natural log function limits us. So we're limited to just it being continuous on the open interval from 0 to infinity. So 3 times natural log plus inverse tangent is continuous on that open interval. Now what about the term in the denominator, that x squared minus 1? Well, x squared minus 1, that's just a polynomial, so that's continuous everywhere. So that's continuous on the interval from minus infinity to infinity. But in this function, the way we're combining them is we're dividing one by the other. So that's going to introduce some issues. So when we kind of put those together, it's good everywhere. Again, we have to go with the most restrictive interval there. So it's good on the interval from 0 to infinity, but we have division, so we can't have division by 0. So we need to investigate, where is that function x squared minus 1, where is that equal to 0? So that happens when x is equal to plus or minus 1. So there's 2 possible x values there where we might be dividing by 0, and we have to throw those out of our interval. And so the way we can kind of notationally denote that we're throwing them out is we put this little like set subtraction sign, and we're going to throw out the positive number 1. Negative 1 doesn't really matter here because it's not even in the interval to begin with. So we're just going to throw out that x value of 1. So another way to write this is we could just write it all in interval notation, where we do the interval from 0 to 1 and then union that with the interval from 1 to infinity. So we've taken our interval 0 to infinity and we've kind of thrown that x equals 1 value out. And this is where our function is continuous. It's continuous on this interval. So on those pieces, on those intervals, there's no jumps or breaks in this graph, but something is happening at x equals 1 where we are having some sort of jump or a break or a hole in the graph. But on those other intervals, perfectly fine. All right, so that's continuous functions. In terms of algebra or regular arithmetic, now let's look at another one and see how, again, how continuity can be used to evaluate a limit. So let's look at the function sine x over 1 plus cosine x as x approaches pi over 2. And we want to calculate this limit. And so to do that, we're going to use continuity. So let's first talk about all the arithmetic that's going on in our function. And then identify the intervals where our function is continuous. So we go through and we just sort of identify the pieces of our function. So in the numerator there we have sine x. In the denominator we have 1 plus cosine x. And we want to identify the intervals where these functions are continuous. So sine is one of our nice trig functions. It's continuous on all real numbers, so minus infinity to infinity. And same thing with 1 plus cosine x. Continuous on all real numbers. And really this is the sum of two continuous functions. So 1, the constant function 1 is continuous, cosine is continuous, so when we add them together, they're both, the sum is continuous everywhere. So there's no restriction for the numerator and for the denominator. Now we are dividing, so that could introduce some restrictions here for continuity. So the interval is minus infinity to infinity, but we have to throw out any x values where the denominator is equal to 0. So we require that denominator function, 1 plus cosine x, it can't be 0. So let's see where that happens. So that's sort of the question. Where does 1 plus cosine x equal 0? And that happens if, cosine x is equal to -1. And that happens, that's one of our sort of important values of cosine. So this might be something we're going to be seeing over and over, so we have this sort of thing memorized. And that happens where? It happens at the odd multiples of pi. And unfortunately, there's a whole bunch of places where this happens, so it just keeps going and going and going. So plus or minus pi, plus or minus 3 pi, plus or minus 5 pi. There's a whole bunch of spots where cosine x is equal to -1. So unfortunately, this function, it's continuous almost everywhere, so at almost every x value, except those odd multiples of pi. So for the purposes of calculating this limit, though, we're doing the limit as x approaches pi over 2. So what we're seeing is pi over 2 is actually in, though, this domain of continuity. So what all of this shows is that our function f of x our function sine x plus 1 plus cosine x is continuous at x equals pi over 2. So we know the function's continuous on for all of those x values except those odd multiples of pi. So pi over 2 is perfectly fine. So what that means is when we go to evaluate, we can just plug in. So we can just evaluate this limit by just plugging in. So I plug pi over 2 into the top function, plug pi over 2 into the bottom function, and then I do my arithmetic. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And I get 1 over 1, which is just 1. So we're using continuity there to help us evaluate this limit. And so, you know, if we use continuity when we're evaluating, we want to state that we're using it, and we want to state why our function is continuous. Yeah, so this function 1 plus cosine x, we're going to talk more about this in a little bit, but this is really the sum of two continuous functions. So we'll talk more about constant functions in the next learning outcome, but you can think of that plus 1 at the beginning. It's just a constant function. And so we have a constant plus a cosine x, so the sum of two continuous functions. All right, so that's looking at functions where we combine them with just usual arithmetic, plus, minus, multiplication, division, that sort of thing. There's one other way to combine two functions, and that's with composition. So first, let's just remember what the composition of two functions is. So we have our definition here. Let's say we have two functions f and g. We can form the composite function f composed with g, and it's defined where we take our input x, we plug it into function g first, and then we take that result and we plug it into function f. So it's sort of like an assembly line. And usually we call the function that we do first, we call that our inner function. And then the one that happens last, we call that our outer function. And when we do composition, because it's like an assembly line, the order that we do everything, the order matters. So if you reverse the order, if you kind of switch the inner and outer function, most likely what's going to happen is you're going to get a different result. All right. So let's just see an example where we do the composition of two functions. So let's say we have the function f of u. So be careful how you say that. We have the function f of u equal to arc sine of u. And we have another function u of x equal to 1 minus the square root of x over 1 minus x. And we're going to calculate the composite function f composed with u. So when we do this, we're going to do our, let's just write out what the definition is. So we're going to do f composed with u. And the way we do that is we plug in x into our inner function first. So we're going to plug x into u first. And let's write in what u of x actually is. It's 1 minus square root x over 1 minus x. And so to finish this off, we're going to take that whole fraction and we're going to plug it into function f. So basically, wherever I have a variable term in my function f, I'm going to switch that with this entire fraction. So I'm going to have arc sine, and then instead of u, I'm going to have arc sine of 1 minus square root x over 1 minus x. And we see that arc sine here is our outer function, and then that fraction is our inner function. So just a little practice doing composition. All right, let's see how continuity works with composition. So we have this theorem, and it really tells us that continuity works very nicely with limits, or continuity behaves very nicely with composite functions. So let's say we're doing the limit of a composite function and the outer function is continuous. So let's say that we know this outer function is continuous at x equals b. If we know our outer function is continuous, well, what can we do with the limit? We can bring the limit inside of that outer function. So essentially what we're doing is we're taking this limit and we're just applying it directly to g of x. All right, so let's see how this works with that function, that composite function we just looked at. Arc sine of 1 minus square root x over 1 minus x. And we'll do the limit as x approaches 1. And so when we do this, we know arc sine is continuous. So our outer function here is continuous, so we can move that limit inside. So we'll have arc sine of the limit of 1 minus square root x over 1 minus x as x approaches 1. And so now what we need to do is just figure out what the limit of that inner function is. And let's do that kind of below. We'll kind of do this separately. So we'll do the limit of 1 minus square root x over 1 minus x as x approaches 1. And so now this is just one of our regular limits that we had been doing in the limit law section. And so our first thing to try is to plug in. So we could try plugging in x equals 1. But if we do that, we get the 0 over 0 form, indeterminate form. So I won't show all of that, but we're going to get a 0 over 0 form if we just try to plug directly into that. So we have to use one of our other techniques. And when you see a square root sign, you should start thinking about the rationalization method that we looked at last time, where we multiply by the conjugate. And that's what we're going to do here. So we're going to multiply by the conjugate of that term in the numerator. And basically it's the same thing, we just switch the minus to a plus. So why does that help us? Well, let's see what happens. Let's actually multiply those two terms now in the numerator together. And when we do that, we multiply the first terms together, we get 1. We multiply the last terms together, we get negative x. And then we multiply the inner terms together, we get negative square root x. And then we multiply the outer terms together in our little multiplication here, and we get positive square root x. And so what we're seeing then is the negative square root and the positive square root cancel out. So that happens a lot when we do this sort of conjugate method of where we have square roots. We get a lot of canceling. And then the denominator, we're not going to do anything down there, so let's just write it as 1 minus x times 1 plus square root x. And then we're still doing the limit as x approaches 1. And then when we look at this, we get more canceling. So it's a lot of fun. You get your red pen out and you see what you can cancel. We already canceled some things, but we get to cancel some more. So we have this 1 minus x on the top. And really that's all that's up there now. Once the dust settles, all there is that 1 minus x term. So we can cancel that out with the 1 minus x in the denominator. So after all of that, we're left with the limit as x approaches 1 of just 1 over 1 plus square root x. And as soon as we do that canceling, we can plug in to try to finish evaluating this. And so we just make note that this is a continuous function at x equals 1. So there's no division by 0. And there's no negatives under the square root. So that's the one thing we have to be careful when we have a square root signs. We can't be plugging a negative into that. And then we have a fraction, so we can't be dividing by 0. So if those two conditions are met, then really the function here is continuous. So it's what that means then for us is we can just evaluate this by just plugging in x equals 1. And so we get 1 over 1 plus square root 1, which is 1/2. And so we've done all this work separately, and now let's just go back and finish up the original problem, which was evaluating the limit of that arcsine function. And let's fill in what we found, that inner limit was 1/2. So we've just essentially moved the limit through that continuous arcsine function, done the limit of just that inner function, and then filled it back in. And the only thing we want to make an extra kind of note about is that our arcsine function is continuous at x equals 1/2. So that's the only thing you need to check is, does this result, when you plug it in, does it make sense? So can you actually plug in 1/2 into the arcsine function? And yeah, we can. Arcsine is defined on the interval from -1 to 1. So we're all fine here. All right, let's try one more example of doing limits with continuity. And well, actually just looking at continuity and how it works with just the composition of two continuous functions. So in that last theorem, there really was no restriction on function g other than that the limit exists. So g might not be continuous in this last theorem, but the limit might still exist. And that's actually what we saw. In this next one, we're going to see what happens if we have two continuous functions. So if f is continuous and if g is continuous, well then, just like we'd expect, the composition of the two of them is continuous. So we're not going to do limits here. We're just going to just identify the intervals where each of these functions is continuous. All right, so let's look at sine of x all cubed. And we see that this is a composite function. And really, when we notice that, we want to identify the outer function, and we want to identify the inner function. So the inner function is usually what happens inside the parentheses. It happens first. So in this case, we'll call it u of x, and it's that sine x function. It's the thing we do first. So it's the thing we first do to x. So we plug x in, it goes right into that sine function. And then the outer function, when you're looking at it, the outer function is what happens sort of on the outside. So it's the last thing we do. And I'll call this f of u. And it's the cube function. So the very last thing we do here is we cube whatever we get from our sine function. So our outer function is going to be u cubed. All right, so we want to figure out what happens when we combine these two functions. Where is the result continuous? Well, u cubed that's just a polynomial, so that's fine. That's continuous everywhere. It's continuous on the interval from -infinity to infinity. And then same thing with sine. Sine is continuous everywhere. No restrictions. So all is good. So when we combine those two functions, the result, by a composition, the result is continuous. And it's continuous on the interval from minus infinity to infinity. So there's really no restrictions here. Both of these functions are perfectly fine. Now in the next one, we have the function natural log 1 plus cosine x. We see that it's a composite function, and we want to figure out the interval where this function's continuous. So we start by just identifying the inner and the outer function. And usually, the outer function happens it's the last thing. It's sort of towards either of the ends. And then the inner function usually happens inside parentheses. So in this case, I would say our inner function might be that 1 plus cosine x. And then the outer function is the natural log. Now, natural log, we know there's some restriction there. So that one is continuous on the open interval from 0 to infinity. So we can't plug negative numbers or 0 into natural log. So there is some restriction there. So this puts some restriction on what the inner function can do. And so 1 plus cosine x by itself, that one's perfectly fine. It's continuous everywhere, but we're going to need 1 plus cosine x to be greater than 0. And that's because our outer function is only defined, it only makes sense if the input is greater than 0. So we need the input of that function to be greater than 0. All right, so let's start putting this together. So our function capital F is going to be continuous on, and we have to again go with that, the most restrictive x values between the two of them. So the restrictions that we're seeing, most of them occur from natural log, so we have to kind of start with that interval from 0 to infinity, but we're going to have to throw out some additional x values if 1 plus cosine x were, say, equal to 0. So we'll see what values we have to throw out in a second. And we looked at this before. So we saw, what did we see? We saw 1 plus cosine x was equal to 0 at, well, let's write it as greater than 0. And that happens only if cosine x is greater than -1. Cosine x is almost always greater than -1, and the only places where that's not true is where cosine is equal to -1. And we saw where that happened before. So those were at the odd multiples of pi. So plus or minus pi, plus or minus 3 pi, and so on. So that inner function is, for the most part, greater than 0, so that's good. But there are some places where it is equal to -1, or where it is equal to 0. And those are the places where we have some issues. So at x equals plus or minus pi, at x equals plus or minus 3 pi, and so on. So those are the x values that we need to throw out. So we're good on the interval from 0 to infinity, but we have to throw out plus or minus pi, plus or minus 3 pi, and so on. So there's a whole bunch of those that we have to throw out. And if we wanted to, we could write that as, just an interval notation, but we'll have an infinite number of intervals there. So I'll leave it like that, where we have the interval from 0 to infinity, and then we're removing those positive and negative multiples of pi. So this function is for the most part continuous. We just had to be a little bit careful for where it's undefined. All right, so that'll end it for continuity for now. And what we're going to see next is we're going to talk about limits at infinity. So first we'll define what that is. What is a limit at infinity? And then we'll see how they're used to find horizontal asymptotes for a curve. So first the definition. So we have a few definitions here, and really just to introduce the notation. So we say the limit of f of x as x approaches infinity is equal to the number L. And what this means is that as our input values x get very large positive, the output values of our function f of x get very close to some number L. So what we're doing here, really what's new, is we're saying x approaches infinity. Right here in our definition here. That's the only bit of this that's really new. And what this means is that our input x gets large positive. So we're letting our input get larger and larger positive. And there's a couple different possibilities for what might happen. Maybe our output approaches a number. So that's what we're seeing here, is the output of our function is getting very close to some number L. But that might not always happen. So another possibility, and we say the limit of f of x is equal to positive infinity, if as our input values get larger and larger positive, the output values of our function also get very large positive. And so we say plus infinity here if our outputs are getting larger and larger positive. And then something similar for minus infinity. We say the limit of f of x as x approaches infinity is equal to minus infinity. And what that means is that, again, as our input values get large positive, the output values get very large negative. So we're using this negative infinity to denote that our output values are getting larger and larger negative. So numerically, what does all of this look like? Well, we've seen how to do limits before numerically. So we have our input values in one column, and then we have the output values of our function in another column. And so as we read down this table, we see that our x values are getting larger and larger positive. So that's really what we mean by x approaching infinity. Just the inputs are getting larger and larger positive. Now in the first example here, we have this function f, and as we read down the table, it looks like the output values are getting closer and closer to the number 2. So we have like 1.995, and then as we read down, it looks like we have 1.999999. And numerically, what this is saying is the limit of our function as x approaches infinity is equal to 2. Now, if we look at function g of x, some other function, we're taking those same input values and we're just plugging it into some other function now. And as we read down the list, what's happening to function g of x? Well, it looks like those output values are getting larger and larger positive. And so as we read down the list, the very last one the output value is 1,250,000. So in this case, numerically, this is where the limit of our function is equal to positive infinity. And then finally, the very last one, as we read down the list here, we're seeing the output values get larger and larger negative. And so we would say the limit of our function h of x as x approaches infinity is equal to minus infinity there. So the output values are getting larger and larger negative. All right. So these are the definitions where x is approaching infinity. We're not going to go through the definitions. They're very similar for where x approaches minus infinity. So there's 3 definitions very similar to these, where all we do is replace x approaching infinity with x approaching minus infinity. And what this means is our input x gets large negative. And we can look at the behavior when that happens. Now graphically, what does it mean when x approaches infinity and x approaches minus infinity? Well, as we'll see next, graphically, x approaching infinity really describes the right end behavior of our function. So you go like really far out into time and you're seeing what your function's doing. Or x approaching minus infinity, this describes the left end behavior of your function. So you go really far to the left and see what your function's doing. All right, so numerically, what does it look like for x approaching minus infinity? Well, on your table, x approaching minus infinity, if you were to do that or think about that numerically, you would just be plugging input values that are larger and larger negative. So maybe you do like, minus 500, then maybe minus 6,000, maybe minus, you can pick anything as long as the values are getting larger and larger negative. So maybe like 70,000. You just keep getting larger and larger negative, and you see what happens to your function. All right, so let's look at graphically what's going on. And really the main story here is that if the limit exists, so if the limit of f of x as x approaches infinity or x approaches minus infinity is equal to some number L, well, we have something special on our graph, and we call that a horizontal asymptote. So the horizontal line y equals L is a horizontal asymptote of the curve y equals f of x if either of those two limits exist and equal L. Now maybe both of them, but only one of them has to equal L. But maybe both. So let's see an example. Let's look at this first graph and see what's happening. So when we talk about x approaching infinity, really we're looking at the right end behavior of our function. So we're looking at what happens as we move very far to the right. And in this case, if we look at our graph, it looks like the value of our graph is getting closer and closer to that line y equals 2.5. So it looks like the height of our function as x approaches infinity here, as we move further and further to the right, is equal to 2.5. Now on the left end behavior, that's where x is approaching minus infinity. So it's going in the opposite direction. And as that happens, what does our function looks like it's doing? Well, the curve looks like it's getting closer and closer to that line y equals -1. And so in that case, we say that the left end behavior and we can describe that as a limit. So the limit of f of x as x approaches minus infinity looks like it's -1. So these limits at infinity really describe, they kind of forget about everything that's happening in the middle, and they look at the extremes, the extreme right and the extreme left. And so judging by the graph here, we say that this function would have a horizontal asymptote at 2 spots, at y equals 2.5 and y equals -1. So it has 2 horizontal asymptotes. Now a function only needs, it doesn't have to have 2 horizontal asymptotes, it might only have 1. And so in the next graph, we're only going to be looking at the right end behavior, just to see another example. So let's see what happens as x approaches infinity. And if we look at the graph, what we see is that it's oscillating, but it's the amplitude, the height of the oscillations is decreasing over time. And so we would say this is another example where the limit of our function exists as x approaches infinity, and it looks like it's bouncing back and forth around that line y equals 1, but getting closer and closer to it over time. So we'd say the limit in this case is equal to 1. And so what we're seeing is we're seeing our function, it oscillates, but the amplitude is decreasing. It's decaying. So over time, the output of our function here is getting closer and closer to the number 1. And so this is another example for what a horizontal asymptote could look like. So this, we would say, has a horizontal asymptote at y equals 1. Even though it keeps crossing that line, that's perfectly okay. It keeps bouncing back and forth. It keeps crossing that line y equals 1, but over time it gets very close to it. So we call that a horizontal asymptote. All right. So just a few graphical examples there. And we'll come back to this and we'll talk about horizontal asymptotes, as we do some of these limits. But in order to find all horizontal asymptotes, you need to check both of those limits. So you need to do both of these. The right end, x approaching infinity, and then you also have to do the left end, x approaching minus infinity. And in what that first graph shows is you might get different results. So that's perfectly plausible. So you want to calculate both of those if you're interested in finding all horizontal asymptotes of a function. And those are the only 2 ways we can have these types of asymptotes, is with the right end and the left end behavior. So at most, a function can have 2 horizontal asymptotes. Might only have 1, might have none. All right, let's look at now, we're going to go through some of our basic limits, sort of our elementary functions, and see what happens with each of these on sort of the extreme ends, the right and the left end behavior. So let's start with our easiest functions, just basic power functions, x raised to the power n. And for the most part, this is what they look like. So in that first graph, that's what they look like if our exponent is n is even. And that second graph, that's what it looks like if the exponent's odd. And we're talking about positive integer values here for our exponents. So let's see what happens with each of these limits. So let's start with the right end limit first. So as x approaches infinity, positive infinity, means we're moving out towards the right. And in this first graph, what we're seeing is the height of our function is just going up and up and up and up. So what that means is the limit of that function as x approaches infinity is equal to infinity. And then we're seeing the exact same thing in the other case. As our input values move further and further to the right, the height of our function is increasing. It's going up and up and up. So in both of these cases, the right end behavior is infinite. So we say the limit of x to the power n as x approaches infinity is equal to infinity. Next, we want to look at the left side, the left end behavior. So let's go to our graph, see what happens in our even case. So as we move to the left, what is our function doing? Well, we go to our graph and we see that it's moving up and up and up. Now the odd case is doing something different. As we move further and further to the left, the height of our curve is actually going negative, and then it just keeps decreasing and keeps going lower and lower and lower. So how the power function behaves depends on whether the exponent is even or odd. So it's equal to positive infinity if the exponent is even. And then it's equal to minus infinity, gets lower and lower, larger and larger negative, if n is odd. So these are sort of the two kind of cases for just basic power functions. Let's look at a few more. So we're just going to go through kind of a laundry list here of just basic functions, our elementary functions, just to see what the end behavior is for each of these. So let's look at power functions with a negative exponent. And again, there's two cases here, n even and n odd. So we're looking at the limit of 1 over x to the power n as x approaches minus infinity and as x approaches positive infinity. So let's start with the right end behavior. Let's see what happens to our function. So we let x move further and further to the right. And what we're noticing in our graph is that the curve is getting closer and closer to the x-axis. So that x-axis, it has an equation. The equation is y equals 0. So as we move further and further to the right on that first graph where n is even, the function is getting closer and closer to the number 0. Same thing in the other case here. Let's look at what happens as our inputs get further and further to the right, get larger and larger positive. Well, we're seeing the exact same behavior. The graph of our function is getting closer and closer to the x-axis. And so again, that x-axis is y equals 0. So in both cases there, the limit, we say, is equal to 0. So as x approaches infinity, as x moves further to the right, the output of this function 1 over x to the power n is getting closer and closer to the number 0. Now what happens on the left? So in both of these, as x moves further and further to the left, the output of our function still gets closer and closer to that same line. So in both of these cases, we have a horizontal asymptote at y equals 0, and it happens to be the same in both directions. So our limit as x approaches minus infinity of 1 over x to the power n, it looks like our graphs are approaching that same line, and they are. So we say the limit's equal to 0. So we have each of these limits, and we just make note that here's an example where we have a single horizontal asymptote at y equals 0. And so the thing to keep in mind with this setup is usually when we have 1 over a large positive number, or just in general a large number, what happens to our limit is we get closer and closer to 0. So whenever we divide a constant by something that's getting larger and larger, we approach 0. All right, let's look at another one, and this is sort of a special case of the power function. This is a constant function. So let's just recall that f of x equal to k, where k is a constant, well, it's a constant function, and what does that mean? Well, whenever we plug in an input, we always get out the same output. So if I were to plug x equals 1 into this function, I'd get out the number k. If I were to plug in x equals to 1 million, I'd still get the number k. So no matter what x value I plug in, I'm always going to get out this number k. And so when we graph this, its graph is nice. It's just a horizontal line. And that's what we're seeing here. So as x moves in either direction here, left or right or left, the output of our function just stays constant, just stays the same. So the limit of k, the limit of our constant function k, as x goes to infinity or as x goes to minus infinity, as we move to the right or to the left, doesn't change. It's a constant, so it just stays k. And so what we see, this is kind of a silly case, but it's the case where we have a horizontal asymptote at y equals k. And it's just because our line is a horizontal line, or our graph is a horizontal line. All right, so that's just another little example of one of our basic functions and what's happening on the extremes, the right and the left. Just a few more of these. So what about our exponential functions? And primarily we're going to be looking at e to the x. So what does e to the x do? Well, if we look at the right limit as x approaches infinity, what we see is that on our graph, the height of our function is going up and up and up. So this limit of e to the x as x approaches positive infinity is positive infinity. And then if we look at the left side, as x approaches minus infinity, what do we see on our graph? Well, the height of our function is getting lower and lower and lower. And it's approaching that horizontal line. It's approaching our x-axis. So we saw this before. It's approaching our x-axis here, which we know has an equation y equals 0. So for e to the x, as we go in the other direction, the limit as x approaches minus infinity is equal to 0. So here, for exponentials, we do have a horizontal asymptote, and it happens to be the x-axis, y equals 0. So when we're doing limits later on, kind of the picture to have in your head is that if we have e raised to a large negative number, the result is going to 0. And if we have e raised to a large positive number, well, the result is going to blow up and it's going to get larger and larger and larger. So it goes to infinity. Well, exponential functions are related in some way to log functions. And so let's see what happens with log functions on the two ends. So let's look at natural log of absolute value x. So I put the absolute value there just because if we didn't have the absolute value, natural log would be undefined for negative numbers. And so the left limit wouldn't make any sense. So just a note. If we didn't have that natural or absolute value, if we were just doing the limit of natural log x as x approaches minus infinity, that doesn't mean, that's meaningless. We can't plug negative numbers into the natural log function. So that would just be undefined. But if we did have an absolute value around that x, then we could talk about the left side limit there. And what we see in either case is that as our inputs get larger positive or larger negative, the output of our function is growing, and it's getting larger and larger as well. So in either case here, as we move to the left or to the right, the log function grows and it gets large positive. Okay, so those are exponential and log functions, and we're just kind of going through most of our elementary functions. And let's look at just a few more. Trig functions and inverse trig functions. So let's look at sine. What does sine do? Well, it just bounces back and forth, and the amplitude of it, the height of it, doesn't decay at all. It just kind of always goes up to 1, then always goes down to -1. Then it goes back up to 1, and then it goes back to -1, and then back up, and so on. And the amplitude, the height of our sine curve, doesn't decay over time. So what the graph of sine does is it just keeps oscillating back and forth with no decrease in amplitude. So we had that graph earlier on where we did sort of have that back and forth behavior, but over time the height of our curve was decreasing and it was getting closer to that line y = 1. Here we don't have that decrease. And so we say that the limit, whether we move to the right or to the left, it does not exist. So DNE does not exist. And this is true for all of our trig functions. So similar limits. For all 6 trig functions. And we know trig functions, that's what they do. They move back and forth. So limit of cosine doesn't exist. Limit of tangent doesn't exist. Secant, cotangent, all 6 trig functions, the limits at infinity do not exist. But for inverse trig functions, some of those actually do exist. And so, for instance, the inverse tangent function, this is the one we'll see most commonly. This one actually does have limits at infinity. So if we look at our graph, if we move to the right, it looks like the output of our function is getting closer and closer to that line pi/2. And so we say the limit at positive infinity is pi/2 for our inverse tangent function. And then same thing for the left side. As our input gets larger and larger negative, the output of our function is getting closer and closer to that number negative pi/2. And so the limit of inverse tangent as x gets large negative is equal to negative pi/2. And so inverse tangent behaves, it has some nice limits here, and it actually has 2 different horizontal asymptotes, y = pi/2 and y = negative pi/2. All right, so these are sort of all of our different basic limits at infinity that we'll be kind of using throughout the course. What we want to do is we want to kind of do some calculations with them, and let's see an example. So in this example, we're going to do the limit of a rational function. So we're going to do the limit of 3x squared minus x minus 2 over 5x squared plus 4x plus 1 as x goes to infinity. And what we're going to see is that this limit is in indeterminate form. And it requires kind of a special procedure on how to kind of do it. So let's just look at the numerator and the denominator of this function. So if we were to look at this numerator, 3x squared minus x minus 2, as x gets larger and larger positive, what we would see is that this numerator would also be getting larger and larger positive. So it's going to infinity. And then something similar for the denominator. As the input gets larger and larger positive, the output is getting larger and larger positive. So if x is large positive, 5x squared is going to be even larger. And so the numerator is going to infinity, the denominator is going to infinity, and so this is one of our indeterminate forms that we're going to always have to deal with. And so the main story here is we do not know what happens with an indeterminate form. The top function might win out, the bottom function might win out, or the two might sort of balance each other out and we end up with a number. So we don't know what happens with this limit. It could be infinite, it could be negative infinite, it could just not exist, or it might equal a number. So the way we deal with it is we're going to introduce this strategy which I call the x to the power n method. And we use this a lot of times with rational functions like this. And what we do is the first step is to just identify the largest power of x in the denominator. And then we're going to multiply both the numerator and the denominator by 1 over x to the power n. So let's see how this works. So we're going to start with our limit, 3x squared minus x minus 2 over 5x squared plus 4x plus 1 as x goes to infinity. We're going to identify the largest power of x in the denominator. So the largest power of x is x squared. So what we're going to do is we're going to multiply the numerator by 1 over x squared, and then we'll multiply the denominator by 1 over x squared. So that's our technique. And then we go through all the arithmetic of just distributing, and we'll see why this works in a second. So right now it might be kind of a mystery. Why are we doing this technique? And we'll see why it works in a second. So let's go through. Let's distribute the 1 over x squared to every term in the numerator. And we'll simplify as we go along. So when we multiply 3x squared with 1 over x squared, the x squareds would cancel and we'd just be left with 3. When we multiply the negative x with 1 over x squared, some of the x's would cancel and we'd be left with negative 1 over x. And then finally, when we multiply it with the negative 2, we'd have negative 2 over x squared. So that's just multiplying out the numerator. What about the denominator? Well, let's take that 1 over x squared. We'll multiply it with the 5x squared. What do we get? Well, 5x squared times 1 over x squared is just 5. The x squareds cancel. And then we keep going. And we multiply the 1x squared with 1 over x squared with the 4x, and then with the 1. So we get 4 over x plus 1 over x squared. So we've gone through and we've kind of multiplied each term by 1 over x squared. Now we want to calculate this limit, so we can use most of our limit laws that we've looked at before. They still apply here. So we can use our limit laws. So we can write this as the limit of 3 minus 1 over x, minus 2 over x squared. And then the limit of the denominator. And then we can go a little bit further and keep breaking that up wherever we have addition or subtraction and wherever we have a constant multiple. So we could write this then as the limit of 3 as x goes to infinity minus the limit of 1 over x as x goes to infinity minus 2 times the limit of 1 over x squared all over the limit of 5 plus 4 times the limit of 1 over x plus the limit of 1 over x squared. And all of these are as x goes to infinity. So we've just used all of those limit laws that we've seen before. So we can split up a limit where we have a fraction, we can split up a limit where we have addition or subtraction, and then if we have a constant multiple, we can bring the constant multiple in front of the limit. So those were just all of our limit laws that we've seen before. Now the thing that's new is that these 1 over x's that we have, 1 over x and 1 over x squared, we know what those limits are. So the limit of 1 over x to the power n, we said that was equal to 0. So this is why this method works, is because each of those limits of 1 over x, those are equal to a number. And that's what's nice, is that 0 is a number. So we can do a usual arithmetic with it. We can add 0, we can multiply by 0, perfectly fine. So when we do this, the limit of 3 is 3. The limit of 1 over x is 0. The limit of 1 over x squared is 0. So in the numerator, we get 3 minus 0 minus 2 times 0. And then in the denominator, we get the limit of 5 is just 5. It's a constant. So the limit of a constant is the constant. Then we have plus 4. And then the limit of 1 over x is 0. So we have plus 4 times 0. And then the limit of 1 over x squared is also 0. So if we do all that arithmetic, we get 3 over 5. And so that's our limit at infinity here. And as we're doing this, we make special notes. 0 is a number. So nowhere in this am I directly plugging in infinity. So I'm not plugging in infinity. Infinity is not a number that we can plug in and do arithmetic with. So why we're using this method is because we're getting a number out. So for instance, this limit of 1 over x as x goes to infinity, that limit is equal to a number that we can do arithmetic with. So we can't just plug in infinity. 1 divided by infinity is not a number, so we can't do anything with it. It's just a symbol. And so we can't plug it in, we can't add it, we can't subtract it. It's just a symbol. So the way around that is to introduce this idea of let's switch everything to a fraction, and then we know the fractions go to 0. All right. let's see here. So we calculated our limit at infinity. What did we get? We got 3 over 5. So what that actually shows us, though, is that this function has a horizontal asymptote at y equals 3 over 5. So, that's nice. Just a kind of a little side note there. And then if we were trying to find all the horizontal asymptotes, we'd have to go in the other direction. Calculate the limit as x approaches minus infinity. All right, so we'll see a few more examples of these next time. And before we get going, just a quick reminder, quick note. I did extend the homework for learning outcome L1. So that was due Tuesday. So you have until Friday to finish it up. So if you didn't finish it, make sure you get it finished by tomorrow. So primarily I did this just for the few people that joined the class late. So they had a few more days to work on it. So make sure you get that done for tomorrow. You have until 11:59 p.m. So get that done. And then we have our next sets of homework, L2 and L3. Those are due next Tuesday. And then our first exam is next week. So make sure you read through the exam setup page on the course website. And then if you have recitation today, we'll be talking about the exams more in recitation today. So and I'll be posting what questions what learning outcomes will be tested on this exam. Just after lecture. So I'm planning on learning outcomes L1, L2, L3, and L4. So I'll give more of a description of that on the course website after class. Okay, so have a good rest of your Thursday. Have a good weekend, and then we'll see everyone in class on Tuesday, next Tuesday. Bye-bye.